We are going to continue our discussion of the definite integral as the area under the curve. For that, we are going to give some examples of different functions that lie above, under the x-axis, or maybe have parts above and some parts under the x-axis. And we're going to see how can we calculate the area under the curve in each of those situations. Then the second part of the lesson is going to focus on the area between two different curves. For our first example, we're going to consider a function that is mostly above the x-axis, especially in the interval where we're interested in finding the area. So the function that we're going to use is the function x power 3 minus x plus 1, and we are asking what is the area in the interval minus 1 to 2. So minus 1 is here, 2 is here. The area that we're interested is all of this. So how are we going to do this calculation of the area? We are going to integrate from minus 1 to 2 the function x power 3 minus x plus 1 with respect to x. And what we learned from the fundamental theorem of calculus is that this is going to be the antiderivative evaluated at 2 minus the antiderivative evaluated at minus 1. So we need to first find the antiderivative, and that is going to be the polynomial x power 4 over 4 minus x squared over 2 plus x. And this is going to be evaluated from minus 1 to 2. Doing the evaluation in 2, we get 2 power 4 over 4 minus 2 power 2 over 2 plus 2 minus, and now we do the evaluation in minus 1 power 4 over 4 minus 1 power 2 over 2 plus minus 1. The first term is 4, and the second evaluation is minus 5 over 4. That means the area is 21/4 or 5.25. For the second case, we're going to consider a function where we're interested in finding the area that is enclosed in a section where the function is negative. So in this case, we're going to use the function x power 3 minus x minus 1, and we're going to calculate the area enclosed by the function and the x-axis over the interval minus 1 to 1. Minus 1 is here, 1 is here, so the area that we're interested is this one under the x-axis. So what do we do? When we calculate the regular integral from minus 1 to 1 of f of x, so x power 3 minus x minus 1 with respect to x, the value that we get is minus 2. So as you can see, the value of this integral is negative, and it makes sense because now my function is not over the x-axis, it's under the x-axis. So it does make sense. But geometrically speaking, we cannot have negative areas. It's not possible. So in the case that we are not interested in just calculating an integral, but we're giving it the geometrical meaning of area, what we have to do is to calculate the area as the integral minus 1 to 1 of the absolute value of x power 3 minus x minus 1 with respect to x. So when we calculate this area, we get an area of positive 2. So in general, when your function takes a negative value and you are interested in finding the area is always going to be the integral from a to b of the absolute value of the function with respect to x. The third case is when f of x changes sign over the integration interval. In this case, the function f of x is changing sign at the point of intersection with the x-axis, and it's only doing it once. So that means that we need to consider the integral of the absolute value of the function as well. The way we're going to do that is, first of all, we need to find what is the value of the point of intersection with the x-axis. We're going to call that point C, and we're going to use technology to find it. C is equal to 1.32, correct to three significant figures. We are going to write the integral from -1 to 2, again considering the absolute value of the function f of x dx. However, because there is a change of sign at c that we know, we can use a property that says that we can split the integral into two separate integrals, provided that the point of split is included in the original interval of integration. So I'm going to integrate my function from the point -1 to c, and I'm going to take the absolute value of the function, and I'm going to add to this integral the integral from c to 2, and this time is going to be just the function dx. Why? Because I know that that integral is going to be already positive. The first integral, however, is going to be negative. One way I can consider calculating the integral of the absolute value of this function would be to swap the order of the boundaries of integration, because I know that the area is going to be negative. When swapping the order of the boundaries of integration, the sign of the integral is going to change as well. So that would give me a positive result. Another way I can do this would be by taking the integral just like it is and then taking the absolute value of the result. Either method would work very well. So what I'm going to do next is I'm going to use option 1. I'm going to swap the order of the integration boundaries for the first integral. So the area is going to be the integral from c to -1 of x power 3 minus x minus 1 with respect to x, plus the integral from c to 2 of x power 3 minus x minus 1 with respect to x. Now, if we do each of these integrals separately, so the first integral is going to be x power 4 over 4 minus x power 2 over 2 minus x, everything evaluated between c equals 1.32 and -1, plus the same antiderivative, x power 4 over 4 minus x power 2 over 2 minus x, this time evaluated between c, 1.32, and 2. When we evaluate this result, we get that the area is equal to 2.1822 plus 1.4322. This way, the total area to three significant figures is 3.61, correct, to three significant figures. Please keep in mind the following note. If we decided that we didn't want to divide this integral into the two parts that we did, and we went ahead and calculated the integral from -1 to 2 of our function, then the result that we would get is -3 over 4. There are two things I want you to notice about this answer. -3 by 4 is negative. Therefore, it could not represent a physical area. Now, there is a way to calculate these integrals using technology, so I'm going to continue to use this integral as example. Like I said, this area would have to be the integral from -1 to 2, but in absolute value for the function. If you don't split it, the absolute value has to be on the function. And since we're going to use technology, we are not going to split the integral. Next, you are going to see how it is done both in a Casio calculator and in a Texas Instruments. The only difference with any other integral is the necessity to use the absolute value in this case. The option to calculate an integral is in your calculators for you to use. You can use it as long as the paper allows the use of technology. You can use your calculator. Unfortunately, your calculator will only calculate definite integrals. So you cannot ask your calculator to give you the antiderivative of a function rather than the value of the integral over a given interval.